talk to people you know. It's always harder to talk to people you know than to talk to strangers. So this is stressful, and I think everything will go good. And I
Got it.
Got it.
think I'll play.
Got it.
Okay. So yeah, this is a strange title, solid state neuroscience. These two things don't go together. So the obvious question is, why do neuroscience in a solid state physics lab? So this is what I will try to tell you about. Okay, so let me start with an analogy. So here we study materials. Prototypical material is iron. Why? Because it has a functionality. It is magnetic. And then, because we're interested in that, we learn how to measure that and make this functionality quantitative, put it in quantitative terms. Then, once we have confronted with that, our job is to try to model that. At the moment that, say, with an Ising model in mean field is the most simplest thing that you can do, you still see that you capture a ferromagnetic transition, and that looks, it resembles what is happening in nature. And then at this point, you said, I understood the basics of what's going on. So this is our bread and butter of every day. So then the analogy is that we also have here a material. This we call it gray matter, but of course, you know what it is. And of course, it has a functionality. We are using that or experiencing that all the time. We are learning how to measure that with more sophisticated ways. This is like a classic one with an EEG that is commonplace, but there is also functional MRIs, and there are optogenetics measurements of individual neurons, and there's a lot of progress being here. So perhaps the time is right to try to understand what is the basics of the thing. And of course, thinking as a condensed matter physicist, you think in terms of degrees of freedom, of interactions, and networks. So going back to the example of iron, we can look at the iron atom and perhaps think that we need all 50-something electrons that it has, and perhaps the 50-something protons that it has, and the neutrons, and all is important to capture magnetism. And we can also think that the FCC or the FCC lattice in iron is also playing an important role. And we scratch our heads, but then we know that just keeping the magnetic moment of the outmost spins and forgetting about the lattice, we can even do mean field, we capture the ferromagnetic transition. So this is now a neuron. So this is the unit in our brain. And the same, we may just simply think that we can represent it as being active or not active. And that has been done with a lot of success. The models that I would like to quote, which is my favorite one, is Hopfield model, which is a Ising model. And most of what came after that are glorifications of this Hopfield model, putting multi-layers, putting convolution layers, and so on. But always the neurons are described as being active one or not active, -1 or 0, as you wish. But neurons are not Ising spins. Neurons spike. They have a dynamical behavior which is not trivial. They emit action potentials. So they are electrically active. They emit a very sharp spike on the millisecond scale. And this sharp spike, when the neuron is activated, travels down the axon and is communicated to the downstream neuron through synaptic connections. And also, we are starting to learn about what is the network of these of the neural networks in the brain, because we're starting to image that, and we're starting to get insight. This is a very active area of research, which goes by the name of the connectome. So, okay, so we want to model neural networks. and we want to model them in their dynamical aspect.
That's a nice question. There is only one axon per neuron.
There is nothing fixed in biology, but most and I'm not the person to ask about those details, but most neurons have one axon, but they have a lot, maybe thousands of dendritic connections.
Yes, but what I mean is that the potential is only paralleling along one of them, or along.
These are not axons, these are the dendrites. So the neuron is excited with currents incoming through all these dendrites. There is an integration going there. When this neuron gets sufficiently excited, it will emit one action potential that travels down this line, one spike that goes down and is communicated to a downstream neuron.
But when you have neural network models, you have arbitrary connectivity of each site to other sites.
Yes, everything is wide open.
Are those connections axons? Can you call them axons? Those JIJs, you have spins are connected by JIJs. Is each JIJ an axon?
No. If you want to make the analogy with the spin model, the neuron is like the spin.
Yes.
Because it's the one that can be active or not active. And the JIJs are the coupling between the neurons.
That's the question.
So the synapse,
Is that an
this-
axon?
so the synapse is the coupling between two. The axon is just a connection.
Okay.
It's just the way one neuron can reach out to another neuron.
So can
Because
you
they are
say that
separated.
If you have a network model that these neurons are sitting on the edge and the synapses are the. Wait, with me? It's as if the.
Okay, let me go on. Maybe your questions will be answered by itself.
Yeah.
This is just a very broad introduction, but which is important nevertheless. Okay, so the goal here is to try to explore neural networks, but in their dynamical aspect, not just like a simple Ising model. So people, of course, have done mathematical models of how neurons generate spikes. They go back to the work of Hodgkin and Huxley, which got the Nobel Prize for setting down a system of differential equations that describe the dynamic of the generation of spikes. And people have worked a lot on variations of these models, and you can obtain all typical behaviors that are recorded in experiments, and then they can put these models into different types of network topologies, and you can try to solve these differential equations. And you know that you have differential equations for each one of the neurons, and you have a very hard time, different time scales to deal with, because this is these are like spikes, and then you want to understand the long-term behavior of this thing or in stable states. So for that, we have neuromorphic chips. So these are neuromorphic computers. So examples of these are the chip True North of IBM, the chip Loihi from Intel, the FPGAs. But these are really conventional computers that have been optimized to run these mathematical models or similar mathematical models. But still, we live in the realm of conventional computers, and to run these models effectively, we need huge mainframes that use a lot of energy and are massive. So nevertheless, you are witnessing every day the progress and the amazing things that artificial intelligence is making. So this is AI driven, but here we really want to understand how neural networks work. So is there another route for this? Not just a conventional hardware to run the models, but can we do something different? So the idea is to make neurons directly in hardware. So you can think of transistors being the basic unit of a computer. How about having a device that behaves like a neuron? So that little device will be a neuron, and you can directly fabricate your neural network by just interconnecting those devices. So that is the idea. And for that, we search new neuromorphic functionalities in materials. So this goes nowadays by the name of membristors and the physical phenomenon of resistive switching. So this is memory plus resistance. And this is a sudden change in the resistance under the application of a strong applied field that is a voltage. So almost 20 years ago, when I joined the lab, I gave a talk on this. I was starting to work on the non-volatile effect. And the non-volatile effect allows to gather a memory. Works like a USB key. You can disconnect it and it stays there. And people are exploiting this non-volatile resistive switching in order to make synapses and to make memories that are inside the cell phones, but essentially to make synapses. That's how you store your memories. And a lot of progress have been made, and a lot of papers have been published on conferences. However, the emulation of a neuron, that thing that can spike, has been much harder and has been, in a way, neglected. So the volatile effect occurs in mod insulators. So this has led to a new and totally unexpected functionality of mod materials.
Can you explain why you are saying that?
Yes. So what is a mod material? So a mod material, if you calculate the bands, should be a metal. But you go to the lab and it's an insulator. So why? Well, here it's again part of our bread and butter of every day. These are strongly correlated materials, and this is a beautiful example of a three-dimensional mod insulator. It's a chalcogenide material, but you have like a beautiful crystal there coming from the lab IMN in Nantes, the group of Laurent Cariot and Etienne Janot. And this material, as you see, at room temperature, you can change the pressure and you hardly see any difference. It is has just some regular conductivity. But as you lower the temperature, if you lower the temperature at room temperature, at normal pressure or at low pressure, you see that this material is an insulator with a very high resistance. But then you apply moderate pressure. This has been done by Carlos Sacha in Buenos Aires with samples from Nantes. You see that you apply a moderate amount of pressure, 5 gigapascal, which is very little perturbation for material, and you see that the resistance collapses by 10 orders of magnitude. So changes in 10 orders of magnitude, you only see in astrophysics. So a condensed matter phenomenon that just shows this behavior to me is still amazing. So you see here very clear insulating behavior and here very clear metallic behavior. But the thing that I want to emphasize most is that how it goes from insulator to metal. And it goes through a first order transition with very strong first order character, and you see the hysteresis loop there. And this, of course, has been fully consistent with my other bread and butter of every day, which is dynamic and field theory, which predicted this metal insulator transition in the 90s, actually during my PhD work. And this is, to me, still the most beautiful demonstration of that. This material doesn't order or anything. It's three-dimensional, has a frustrated lattice, et cetera, et cetera. Okay. But coming back to what we do is, well, this material has been fabricated by this group of colleagues in Nantes, and they were applying strong electric fields to that. So you apply a strong electric field, and what you observe is that the resistance of the system suddenly collapses. When the applied voltage goes away, it recovers to the original value. So that is why it's called a volatile resistive transition. And you can repeat this thousands of times and you get perfectly agreement in the data. There is no variation. This is a genuine feature of the system. So as theorists, we try to model this, and this is the work done with Pablo Storial, which was at the time a postdoc here. We started modeling that. And of course, this is the problem of out equilibrium mode transition. So we have a mode insulator, and we want to observe an insulator to metal transition, applying a voltage that will bring the system totally out of equilibrium. So it was really hard and required all the development of DMFT to get insights into the metal insulator transition in equilibrium. Now you can put it out of equilibrium. And of course, we are making progress with that, and people are very interested and advances being made. But still, to capture the details of this transition out of equilibrium remains a challenge. And there are many open questions that I can tell you about. But in any case, to catch up with the experimental progress and we wanted to understand, we said, okay, let's do something very simple, which is a resistor network. So this is a network of resistors, and each side of the resistor network, each resistor could be a metal, could be an insulator, and we apply voltage, and we solve Kirchhoff law, and we apply voltage there and here, and we model this, and we sort of obtain that this collapse should go through a filamentary formation.
Excuse me, Marcelo.
Yes.
What is the connection to the hysteresis effect? It's this.
You'll see. You'll see. Yeah. For the time being, I'm just saying that just the units here, the resistors, can be metal or insulator. So they start all being insulator because this is a mode insulator. And then at some point, the metallization forms a metallic channel of conduction. And of course, when you percolate, the resistance goes down. Okay. I'm not giving much detail. We're sort of in the introduction still.
But
So
here you have no, sorry. Here you have no hysteresis in the phenomenon.
I'm getting to that. I'm getting to that. Hold.
Okay.
2 seconds. So of course you may say, well, come on, this is just a resistive collapse. It's a percolation. This is not so compelling. So how about a non-trivial validation? So then comes the insight from DMFT. We know that it's a first-order transition with hysteresis. And if we talk about a first-order transition with hysteresis, we talk about metastability, and it's a famous coexistence of a metal and the insulator. So from this insight of DMFT, we imagine that if we have a mode insulator as being the stable state, somewhere in some phase diagram, a correlated metal should be in a metastable state. So then by applying strong electric field, we sort of promote parts of the material to go from the mode insulator to the correlated metal. But then if this is metastable, there should be a barrier of stability, and this system should have an associated time to relax back to the mode insulator. So this is a characteristic time. So can we see that in the simulation? So then if we apply a voltage during a very short time, which is shorter than the time that you need to generate this percolative filamentary path, then in a small voltage time, you will have partial phase transformation inside your material, but then that will relax back. If you come with another pulse, and the time between the 2 pulses is shorter than that relaxation time, there will be a cumulative effect.
Moi, c'est moi qui faut que je réponde. Hein? C'est le neurone, putain, je savoir.
Okay, so as a function of this time in between, yes.
How do you predict the relaxation?
At this time, though, we don't predict, we just assume there is some stability here with some characteristic time. So we modeled that with the probability to go from one guy to the other with the overcoming the barrier, and it's a potential barrier given by the potential, the difference in this energy. So these are parameters at least. But once you pick them, then there is a time, a characteristic time. So if these pulses are frequent enough, there will be a cumulative effect. And after so many pulses, you will have the collapse of the resistance. So since Pablo is really an experimentalist, he went to NUT, did a second postdoc there, did the experiment, and showed that in fact, indeed, if you apply pulses, after so many pulses, the resistance suddenly collapses. Now, when the resistance suddenly collapses, then the applied voltage generates a spike of current going through the material. And that was the first aha moment. Because this is exactly what neurons do. As I said before, a neuron is a cell. Cell, like all the cells in your body, it has a nucleus, has a body, but it has electric activity. That's what sets it apart. And it receives input through the dendrites, which are spikes incoming, spikes of current coming in. There is an integration, and then the emission of this spike down. So you see that this is like what I just showed you before. The simplest model that one can make of this qualitative behavior is actually introduced by a French couple, Louis and Marcel Lapic, more than 100 years ago, which is amazing. I think it's called the leaky integrate and fire model. So in this model, you have the neuron and you have spikes coming in, and there is a relaxation effect too. So you see the first spike coming in that is integrated by this neuron. So the potential in the neuron goes up, integrating the delta goes up. Then in between the pulses, the voltage on the neuron relaxes, but then another comes in and the voltage, it's integrated and comes up, and then another one comes in, and it's very reminiscent of what I told you about these spikes changing the material. And eventually, if these incoming spikes become frequent enough, the integration goes up, you overcome a potential, a threshold, and when you overcome the threshold, this neuron emits an outgoing spike here. And this outgoing spike is communicated to the next neuron. So all this was put into a firmer ground, on a detailed ground on this paper that was published. And the original work was in 2013, this is 2017, and we have to keep that silent because we filed a patent. And I was very happy to have a patent as being a theorist for a leaky integrate and fire neuron made with more material. Okay, so since then, it's been really a lot of activity going on. So I started a collaboration 4 years ago with a group of Ivan Schuler in San Diego, funded by the Department of Energy, and Lorenzo, who was a postdoc until a few weeks ago, was part of that project. And I joined Ivan Schuler that was visiting a few years ago, and I met him here in Orsay. He is running one of the best labs in the world to fabricate some classic Moore materials, which is vanadium dioxide, VO2 and V2O3. So he can fabricate very high quality thin films. So thin film is necessary to do devices. So these are the devices that one can build. So this is a thin film of VO2 of very high quality. On top of that, you deposit electrodes, gold or titanium electrodes, and then you apply voltages on these two electrodes, and you can observe the resistive breakdown of this material.
Excuse me, Marcel, what about the temperature? You don't need helium for this?
This is room temperature, but you can also investigate as a function of the temperature. But in any case, it works at room temperature. VO2 has a methane transition, first order, at 60 Kelvin, 60 centigrades. So it's very convenient for it. So we amuse ourselves to do these simulations and to try. We have very strong interactions with all his experimental group, trying to understand and make sense of very unusual behaviors that we observe, pushing these mod insulators out of equilibrium and doing all type of experiments. And this also led to some theoretical work of Rodolfo, with my student here, and he will be defending his thesis at the end. So he has been doing a lot of work in the modeling of this phenomenon. Okay, so this is great, but you may say, okay, you want to fabricate neurons and you want to use more materials. Why don't you use just conventional electronics? And you don't need the best people in the world to fabricate thin films. And of course, you can. You can fabricate everything with modern silicon technology. And this is an example of an integrate and fire, an adaptive exponential integrate and fire neuron circuit. So you look at that and you said, okay, it's not so simple as this. So in fact, it's quite complicated, but it can be done. Of course, the problem is that it's pretty complicated. You need many years to develop. And then once you do it, it's in a chip and you cannot touch anymore. And it has a certain degree of complexity. So can't we have the best of both worlds? That is, keep the simplicity of mod memory stores, but also have the reliability of conventional silicon electronics? And the answer is yes. And this was the second aha moment. The second aha moment was to realize that there is a conventional electronic component, which is the thyristor, which I learned it in high school, because at that time, it was not only digital electronics. This is a very simple device. You recognize a little bit of the diode symbol, and you see PN junctions. So a diode is a PN that only permits to conduct in one direction. Was the first junction they invented. Then they invented Shockley, Bardeen, and Bratan, invented a PNP transistor. So it's 3 junctions, P and P. And then, of course, you can amuse yourself to put more junctions, and this is a PNPN. The interesting part is that here you have 2 diodes, one after the other. So you would expect this to conduct. But then there is an NP junction there, and that NP junction is in inverse. So it doesn't allow the current to be conducted. So that's why when you put it in direct, the thyristor still does not conduct current and has a high resistive state. But it has a threshold, and that threshold is when you push it beyond a certain applied voltage, or you can control that through the gate, where the system, this depletion layer becomes filled, and when it becomes filled, the hosting conducts, and the system has a very strong transition from a high resistive state to a low resistive state. But the key insight was, besides that, is that this system has hysteresis. To relax, you have to lower the current beneath what is called a holding current, where this depletion layer is formed again because there is very low density of electrons. So there you have hysteresis, and this hysteresis is qualitatively the same as what we observe in more materials. So it was, okay, if we can make a neuron with a more material, we should be able to make a neuron with a thyristor. And the answer is yes. And the thyristor, when you combine the thyristor with one resistor between 2 of its 3 legs, it becomes a memristor that can switch between high resistance to low resistance with hysteresis. So this is the integrate and fire model where you have a current that is integrated by a capacitor. Initially, the memristor is open, so there is no current here. All the current charges the capacitor. The charge in the capacitor raises the potential in the capacitor, and when the potential in the capacitor reaches the threshold of this memristor, then the switch goes down. The system is conductive, and this capacitor discharges very fast with a very fast time constant through the memristor, and crucially, the memristor remains closed until this capacitor empties its charge when the current goes down. So we argue that this is the simplest, the minimal conventional electronic model for a leaky integrated amplifier, because you have just one and only one component for each one of the three functions that you need to get a leaky integrated amplifier model. Integrated with the capacitor, it integrates charge. The resistance will leak the charge, but then the thyristor, when it reaches the threshold, it will fire and get the leaky integrated amplifier. To demonstrate this more evidently, this is a recent work with a group of Ivan, and you see this is done with a mod material. This is a V305, and it has an IV characteristic with a high resistance, low resistance, hysteresis, and when you apply voltage, you get spiking, and this is done with a memristor. This is work done with Jamin Wu, my student, with Olivier Schnegans and Kang Wang at the lab. And you see here the IV characteristic with the hysteresis and the spike generation that looks qualitative like that. But here you need to have know-how for film deposition. It's very hard to fabricate consistently. You need lithography, you need sputter and PLD, blah, blah, blah. You don't have a theory, and thyristors are available online for next day delivery. It just costs pennies. They always work. They work at room temperature. And the only thing that I tell Jamming to be very careful is that when one thyristor is burned, just throw it away and don't mix it, because it costs nothing, and that is the real problem. So we have to always know that it works. So in the years since this setting up this new type of memory, we did a lot of work that has been very productive. Yes.
Just to be sure I understand, the thyristors you buy, are they silicon?
Yeah, you buy it. So it looks like a transistor.
Right.
You can also fabricate that in PLSI, so there are no real limitations for that. Okay, so we done several works. These are two that I'd like to highlight. I just wanted to publish in Frontiers of Neuroscience and also in Physical Review to show that this really should talk to the two communities. And this was the realization of a classic model of detection of the directionality of sound. And the real goal of this was to show that we can interconnect very easily our neurons. These are all identical neurons, this basic unit that is interconnected just as Lego blocks. So you can really fabricate networks very compactly and very easily. And this is a second work where we just address a model of a recursive neuron where one neuron just takes back part of its signals and puts it back in. Recurrent networks is a very hot topic. So that was the main interest. And this is perhaps the minimal network that one can do, which is just one neuron that connects back to itself, but it spikes. Most of the work in recurrent neural networks are done again on Ising types of activation. This is really dealing with spikes. And the amusing thing was that we could make contact with some experiments. This is you can find a dynamical working memory because you have the initial state, which is without spikes, with an applied current that is not enough to apply spikes, but then you come with an excitation peak there, an excitation peak, and the system starts spiking. And then if you excite it again, it goes to a higher rate. And then you can de-excite it, and you can control this dynamical state characterized by a frequency, an activation rate in this discrete manner. And this is supposed to be, some of the mechanisms that allows you to fixate your gaze. So you keep your face straight, but then you want to look there. So you have to push your eyes with the muscles of your eyes to look in some particular direction, and you have to keep those muscles excited at that. And then if you want to change your gaze there, you have to adapt the amount of activation that you give to the muscles in your eyes. So these are that's one example. In this paper, we also compare some systematic application of pulses, but I just don't want to deal too much here, just to show you that I was very excited to be able to fit experiments of a recent paper on biology that found these recurrent circuits. So it's quite exciting to be able, with a condensed matter system or an electronic circuit, to fit experiments, not of condensed matter, but of neurobiology. Okay, but I don't want to spend much time there. I want to really tell you what we are doing now that is really been very exciting. So this is another classic problem of neuroscience, of theoretical neuroscience.
Sorry, Marcelo. Just one question. Nowadays you are doing that with discrete components. Would that be easy to do integrated circuits with series of neurons connected?
Yes, of course you cannot do millions. I mean, to do that, you have to change the technology. You cannot do discrete components. You have to go to VLSI. We have a paper already published on how to implement this in VLSI. So a priori, you can do anything you want. But our idea here is just to learn in a constructive manner, not go to a million neurons, but just to remain at a small scale where we have full control and can understand how neurons talk to each other. So that goes to trying to understand what is called the neural code, which is how does the brain code with spikes. So that is the
Okay, I understand the point. we did that at the beginning of electronics. It was the same before.
Okay. This goes. Neuromorphic engineering has a long history. It starts. It became a more mainstream with the work of Carver-Mead in the 80s, but there is even work before that. Yeah, this is not. Yeah, but as far as I know, this minimal circuit was never mentioned. Okay. In any case, what we are doing now is we're trying to capture more complex behavior in our system. And then I look into models of bursting neurons, and the classic model from neuroscience, theoretical neuroscience, is the two-compartment Pinsky-Rinsen model. So this is a schematic. So they have one compartment for the dendrite and one compartment for the soma. This is the body of the cell, and this is the incoming of the cell. And this model is not so simple. These are the differential equations that you need to solve, and they are like and this is already a model that is simplified from a previous model that had 19 different equations. So you can see also the amount of parameters that are there. So it's pretty hard to try to take this as a stepping stone to build neural networks and to simulate that and to keep all that under control. With timescales, the more neurons you have, the scaling up of the system is the precise scaling of the system is very hard because you're dealing with spikes and you're dealing with long time and you're dealing with a high connectivity, et cetera, et cetera. So nevertheless, when you read about bursting neurons, what they tell you is that on the basic models, you have to add a second time constant. So we had this circuit. The simplest model, the simplest way to add a second time constant is by adding an RC circuit. R times C gives you a new time constant. So we just appended this circuit with this and make the analogy of a soma and a dendrite compartment. And we started exploring the dynamical behaviors, and we observed this for different dynamical behaviors. This is called tonic spiking. This is like the regular spiking. This is fast spiking, which goes discontinuously from here to here. Suddenly the system starts spiking very fast. And then these are two different bursting behaviors, which we observed. Now, question.
Yes. So what you are saying is that now the advantage, so everything could be solved with plenty of differential equations, but it is very hard. So like this, you capture the essential mechanism of.
I'm saying less than that. So I'm saying that you can take the theoretical neuroscience route and write a model that is connected to biology with the biological realism and try to capture what is each one of the ionic channel doing. And people do that, and that is very, very important and useful. But I said, if I want to go ahead and try to build networks, I need to simplify. So this is a way to simplify. If you want, it's like, okay, you want to understand a solid, the cuprates, you can do the density functional theory of the cuprates with all the atoms and the positions and the structure, or you can do Hubbard model. And probably you will not learn nothing from either way.
And if you do the equations of the electronics of that, are they the same?
I'm not doing the equations of the electronics. That's very important.
Experimental.
What I want to do is hardware.
Yeah.
So if I can build on an analogy going on with the Hubbard model, we don't know how to solve the Hubbard model, but we hope to fabricate a quantum computer before solving the Hubbard model. And then the quantum computer will show you the solution of the Hubbard model. Here, in a way, we are building a neural computer. So we want to interconnect neurons that behave like what we think neurons do, the same way Hubbard model behaves like what we think atoms do or electrons do in a solid. So here, we're sort of doing that. We want to fabricate a neural simulator, if you want, at a scale where we keep full control of it. So confronted to this, it was very amusing when we found in the literature that bursting biological neurons can be treated with neurotoxins to see what kind of different dynamical behaviors they have. And you can see that qualitatively, they look a lot like ours. So we change time constants. In the experiment, they change neurotoxins, and they modify, alter the spiking behavior of a single neuron, and we can see that there is some qualitative resemblance, not only with respect to that bursting mode, but also regarding this bursting.
Okay, I'm sorry, it was
Yes.
so fast. Can you come back? Because I don't, so I understand in the first experiment when you're applying involved, so you only see one of the time constant, but then what happens?
No, this is the scale. This is not, this is a scale So under this will become very clear. These are just modes of spiking of this circuit.
Okay, because I see clearly the two-time constant, but I don't know how you obtain this kind of.
Oh, it's non-trivial.
Okay.
It's non-trivial, highly non-trivial. So what people know is that if you start from a spiking model, you need to add another time constant to make it burst. So that's what we did. We added, and we observed that it does burst. If you don't have this, you just close here. The only thing that you observe is this spiking mode. But the moment you add this second one, you see all these things appearing.
Can you just say why is a short and why is a large time constant?
Why there's a short and what?
On the left side.
Yes.
So you have what is you have RTL and
Yes.
the one, so
The short time constant is the product of RS.
yes, okay.
So essentially what you can see is that
And
on a transient, the capacitor is discharged.
okay.
So then this guy, when it starts conducting, is discharged to ground. But this capacitor is small and very quickly it charges. When it charges, then this potential is not ground anymore, then this thing stops. But then the moment it stops, this capacitor discharges very fast because it's a fast time constant, and then it charges again and you go on. So you create an instability there, and that is the origin of the fast spiking, and then around that appear the other modes. They appear, since this is sufficiently simple, just by modifying that time constant and using current and that time constant, we can explore the whole phase diagram. So theoretically, when you are confronted with this Pinsky-Rinson model, there are so many parameters and you can explore everything. Here we have something that has been highly simplified, so we can easily have a bird's eye view and obtain this phase diagram where we have tonic spiking, fast spiking, and these two types of bursting, which are there, which behave differently in different regions of the diagram. So another amusing thing has been also to go to see experiments, and this is a pacemaker neuron in the substantia nigra, if I remember correctly. So this neuron will generate spikes at a constant rate. That's why it's called a pacemaker. But then you apply again a neurotoxin and you make it quiet. It just stops spiking. But then you can inject current to that, and you can inject current and increase the current. And what you observe is that this neuron starts spiking with bursts, short bursts, and this short burst becomes more frequent. And then the short bursts becomes even more frequent. And then eventually they become fast spiking. And it's quite interesting to see that this is consistent with this part of the phase diagram, where we start in a state where the neuron is quiet, but then we apply current, exactly the same as this. We don't change anything else. In this experiment, only current was increased. So here we are increasing current, and we go through these three stages. So now I have to make a confession. So about a year ago, I fell victim of a theoretical physicist midlife crisis. My friend Pablo, who was doing most of the experiments, he went to the industry. So I said, what do I do? And then instead of buying the red convertible, I bought myself a lab, of course, thanks to Pascal and the support of the lab. And I started a new life as an experimentalist. So this is how my new
midlife crisis is a little bit optimistic. You're making yourself younger than you are.
Let's keep this. Okay, so then this is how it looks. This is my student Jaming sitting there. These are how the experiments look. Some it's more messy than that, but it doesn't matter. And just something that I want to share, that it has been, when I saw this, I said, okay, this is exactly telling what is my state of mind respect to this new life is, this is the blackboard of Richard Feynman that they took a picture when he died. So he died, and this was his last blackboard. And then in the blackboard, you can see that he had written on the top, what I cannot create, I do not understand. So this is exactly my feeling. I want to fabricate that, and the belief is that if you fabricate this, you will get further insights. Okay, so the official talk can be considered done, but I still have a few minutes, so I will want to devote, since I'm doing this talk here in a friendly place, I feel sufficiently courageous to do some speculations here. So, okay, we do solids, so let's start with the lattice of atoms. So these are atoms separated by the interatomic distance, the lattice constant. To a lattice, you can apply a pressure. When you apply a pressure, the lattice compresses. So you have pressure, and 1 over A is 1 over the volume, and is the density. So you apply pressure, 1 over A goes up, the density goes up. That's any normal solid. So we look at this, and how about thinking of this as a time lattice of spikes, where the interatomic distance can be one of these typical variables in neuroscience, which is the interspike interval, or the period tau between spikes. And the same way you apply a pressure, here we apply a current. And the same way the density increases, the frequency increases. So we can just be bold and say, how about if pressure is like current and density is like frequency? So PV diagrams tell us about different states of matter. We learned that in school, but here, IF should also tell us about the states of this neural temporal matter. Moreover, there is an equation of state, which we learned in school, P times V equal a constant. This is an ideal gas. So an ideal integrated and fire neuron has also I times period is equal to a constant. It's very trivial to see that, to derive. And the period is 1 over F. So 1 I times 1 over F is like the same as PV is equal to a constant. And this is an ideal neural model. So a neural model is like an ideal gas model. And we may try to go on and think of correlation functions and think of response functions like the compressibility. So this is the compressibility of a solid, the NDP, basically how much the density changes when you apply pressure. And that is the observable that will predict phase transitions. That is what goes critical when you're approaching a transition. So I talk about, phase diagrams where we have the control parameter current here as the pressure. And then here for water, you have temperature as a control parameter. And I introduce this control parameter tau s, a second variable, could be others. But then we look at this problem with more detail, and you see that the frequency versus current of this integrate and fire neuron, this is the limit of this thing going to 0. So you can think of that just being directly shorted there is in the integrate and fire, has this thing that is fit with the predicted behavior of a leaky integrate and fire. That's the red curve. And you see that in this regime, where there is this dot, you have a solid with spiking, very regular spiking. But then when you go there, when the FDI becomes divergent, like a compressibility that diverges at a phase transition, you can think of this as a melted solid, and you see that the regular spikes are no longer regular and start fluctuating all over the place. This is literally this morning, Jiaming obtained the G2, which is the structure factor. In this case, you see the structure factor is a bunch of peaks because it's a structure in time. So this is the G2 of T, not the G2 of R. And then this is in the melted solid state where you see that this thing doesn't go to zero, goes to a very low value, which is basically what is the probability of finding one or two of these guys superposing each other. And since we're in a condensed matter physics lab, it's interesting to see that this is how you talk about a liquid solid transition. This is a solid state of niobium, and this is a liquid state of niobium. So you see that we also have the melting of these solid states. Phase diagrams, and then we can think of all these different behaviors at different states of matter. But then I will go one step more, which is two-body interactions. So then if I have two neurons, the neurons, this in white, the neurons can inhibit each other or can excite each other. These are the two things neurons do. One excites another or one inhibits another. So here are two neurons interacting, one inhibiting the other, and these are two neurons, one exciting the other. And this is a simulation where we start with the two neurons spiking at the same time, are trying to inhibit each other. So if they're trying to inhibit each other, clearly they don't want to spike at the same time, because I spike, I'm inhibiting the other. So then when I spike, you don't spike because I inhibit you, but then when you spike, you inhibit me. So these peaks that start at the same time eventually separated. This cannot be seen very clearly, but they separate, they repel each other. So the state here is like a repulsive state. It's like the blue, which is one, and the red, which is the other neuron, repel each other, and these two lattices separate and conform what one can consider a sodium chloride lattice. On the other case, if one excites the other, and you start with this state where they are separated, what you see is that after a simulation, they superimpose. Why? Because one is exciting the other. So if I fire, I make more likely that the other will fire, and vice versa. So they try to fire in unison. Here they are firing in unison. So it is like they are superposing. So they are like a dimerized lattice. They get together. They attract.
Excuse me, Marcel.
So
I have a silly question. Can you is it possible that one excites but the other inhibits? I mean, it's not symmetric, like somehow.
that's an interesting possibility that I have to think about.
Oh.
I have not. I don't know. Okay, so then, and this is becoming higher speculative, perhaps we can think of the dynamical neuronal states in time. These are, of course, mental states like sleep wave, heartbeats, not necessarily in the brain, walking, persistent thoughts, or even what happens while you play, or when Mark plays a back fugue. Can we think that being analogous to states of matter in space, like we think of a solid, a liquid, a superconductor? So these are mental or neural dynamical states that people measure. These are things that we're starting to fabricate, measure, and try to make sense and understand. So I argue that we can extend the notions of a susceptibility to predict phase transitions. So can we eventually define a mental susceptibility and can be used as a diagnostic tool to predict how likely one is to have epilepsy or to suffer for Parkinson or a heart failure or whatever. So that is all. I thank you very much for your time.
Okay, thank you very much for this very stimulating talk. So perhaps indeed what Ines is proposing would be a source of frustration. Could also retransmit the concept of frustration to mental frustration at the end of it. So
I mean, in the beginning of theoretical neuroscience, there are people like, for instance, Polinsky, that you look at those papers in the 90s coming from statistical mechanics or condensed matter, and you see that their models are like magnetic models when you have up and down spins and ferromagnetic and antiferromagnetic interactions. So of course you can think of frustration.
There's spin glasses and many states.
Oh yeah, the Hopfield model
Spin glasses.
is the model for associative memory. And when you go beyond its capacity, what you have is pretty much a spin glass state.
Why do you mean beyond?
Oh, because in the Hopfield model, it's basically a recipe how to have local stable minima. You choose, it's a recipe to choose the JIJs to have local stable minima. For instance, the simplest one will be if you put everything positive, or if you get everything positive, you have a ferromagnet, or everything negative to have a ferromagnet, you have only two states, everybody up, everybody down. But then if you start, and if you do everything positive, then you have antiferromagnet, null state. So these are states of the system that you can encode playing with the JIJs. So Hopfield model gives you a recipe for those JIJs to encode locally stable minima, and then you say that is the memories. And since they have basin of attractions, this is a model for associative memory. But then if you try playing the game of putting more and more metastable states, at some point, nothing becomes stable anymore. And that is a spin glass state where it's a complicated landscape and the system never stops relaxing. So there's a lot. I'm not the expert here. The experts are the guys at the
Is liquid.
Model for brain?
Hmm?
So you think that the spin glass state with all these minima is not a good model for brain?
Well, it can teach you some things, but I mean, the Hopfield model has made a tremendous advance and was extremely popular in the 80s, in the 90s, and it's at the, to me, it's at the basis of all the model developments in that part of artificial intelligence.
well, we had
But it's a model of icing. So I want to go.
Too simple, but for
Well,
a lot of learning algorithms, maybe I'm not.
Yes, you can do a lot. But the point is that neurons spike, they have the dynamical behavior.
So you introduce.
So why do spike? Also, from an energetic point of view, if you really want to do applications, you can hope to, so the typical comparison that they do is, okay, AlphaGo, a supercomputer, has beaten the Korean super champion of Go. So a computer can beat a human at Go. But then you need a huge mainframe that uses, there are thousands of processors at 100 watts, so you have at least kilowatts, probably megawatts. The brain uses 10 to 20 watts. So you are 5-6 orders of magnitude different. Is that because of spikes? If you do spikes, then the system is not using energy until it has something to say, until some input has come. So the hope is that spikes will dramatically decrease the power requirements. But then we don't know how to, we don't have a Hopfield model of spikes that works with spikes. So how to be able to control, to fabricate any function that we want using spikes.
I think Henri had a question.
Well, completely different. The question is, do you expect the neurons, well, what is the situation in biology? Are all the neurons identical, or are there differences associated with the time constants that you are labeling from the start?
Yeah. Of
If
course.
there is a differentiation, it means that the problem is more complex in that sense than a simple easing model.
Of course, in theoretical neuroscience, there are models that are realistic and models that are more qualitative.
Yeah.
Same as in physics, in condensed matter, that we have realistic theories, density functional, and then model Hamiltonians. The reality is, again, same analogy. It's like there are all different types of neurons. Of course, they're all always get schematized as this drawing that I showed with a body which has dendrites and then an axon and connects to another one. So that is the prototypical situation, but there are many, many different things. And neurons do different things. There are some burst, some don't burst, some do different spiking modes. So biology is very diverse, but typically you see that. So the logic is, of course, I'm not claiming that I do anything realistic. In a way, we are doing like the Haber model, but not just mean field, but dynamical mean field. I'm making now the connection. So in a way, you see, this is bringing in dynamics with respect to treating neurons as icing spins.
Yeah, that's
Which
what you're doing
means
is looking at the local behavior on a single neuron as a function of time, and you see all these different phases of
Yeah,
spiking and
but of course, this is just warm up to try to build networks. So what we want to do is build networks and learn how these networks can be made to function. And of course, you can do a lot with software. So this is a different route, which I can discuss the advantages and the drawbacks of this with respect to software. But of course, there's a lot of simulation in software, and you can do, a lot of people do. This is different.
When you play with the time constants, what will be the analogy? I don't know if you know that the analogy, the physical, the biological.
Well, that's an excellent question, and I'm not the person to answer that, but I just pointed out that just discovering this, because of course it's not my education, I've seen that in neurobiology, they use neurotoxins to modify the spiking modes of neurons. So my guess is that they may be affecting that. They may be affecting the way they generate the spike is by affecting the time constants of the different ionic channels. So at the end of the day, these are relaxation. If you leave the channel open, more open, it will decrease faster. If you suppress the channel, it will take more time to relax. So my guess is that it may be that. But this would be exciting to start talking to chemists, to neurobiologists, and try to, in a way, this is thinking of neurobiology differently, more like we do, have a phase diagram and try to see if different states can be, induced, or can you define susceptibilities?
There was a question by Corentin.
If I'm not mistaken, spiking neurons are a specific type of neuron, and there's a whole zoo of other things which are less studied but common. Have you considered making use of your extensive knowledge of like phases of matter and things to address different types of neurons?
Well, I know, or I should say, I heard that there are neurons that don't spike in a very early animals, so or living beings, but that they don't spike. But I don't know. They still communicate electrically, but I don't know. I'm amusing myself to discover that. For instance, I asked myself, which is the smallest neural network, spiky neural network that exists in animals? And then it turns out that there are sub-millimeter worms that are apparently is the most common thing in nature, and they have about 200 spiky neurons. Then you have the jellyfish that have already 500. So,
do you hope to be able at some point to reproduce some complex things that can happen to the brain? For example, Alzheimer, like what Alzheimer does to a brain. Would you reproduce it with a network of split state?
okay, the brain has about 90 billion neurons and 10 to the 15 synaptic connections. So we are, as everybody else, way smaller. We don't even have the proper technology to try to go large.
Yeah.
If you want, you're talking about water, viscosity of water or properties of water going turbulent or whatever, or evaporating. And we are talking about how a water molecule interact with another water molecule. And then if we start putting water molecules together, will they try to attract and form a droplet or not? So these are like why the different energy states.
You maybe could have a minimal model. Or
We're trying to understand why spikes and how spikes interact and how things emerge out of that. But there are problems at much larger scales.
Okay, there's one last question, please, because afterwards I think we.
Question together. So first, this reminds me somehow the flock is, like the phase transition induced by the time force, like for each flock it.
Yes.
I don't know if you talk about this.
Yes, of course, because at the end of the day, a neuron gets excited by incoming sound. So simplest thing, of course, is you have a neural model and you excite it with a constant current, but you can excite with spikes. And of course, you do that, and that demonstrates, for instance, the properties of the leaky integrate and fire and so on. You can remember that in the beginning, where we started with the mod materials, we applied spikes. We didn't apply constant value of the current. We applied spikes and saw that thing. So of course, we do, but depends on the problem we want to address. So if it's just exploring the genetic behavior, it is easiest just to keep the constant current, because everything brings in a new parameter. If you want to use, you have to excite with periodic excitation. Again, you not only have the amplitude, but you have the frequency, and so there are proliferation of parameters everywhere. So depending on the problem, but if you're interested in that, I can tell you about very cool things.
Yeah, and rapidly, the question of boundary conditions, the analogous of boundary conditions, because this is important also for phase transitions. We know on the mesoscopic scale that if you have nanoscopic system, phase transition can be affected by the size. So what would be the analogous here for time boundary? I don't know if you address the number. This is we can discuss about it later.
Yeah. I don't know. I have to think about that.
Okay.
How to enforce boundary conditions. I mean, of course, you have boundary conditions in a solid. How to enforce
For the time.
in a plan. I think that you have to, as you correctly guessed, a periodic thing with a very long period, then at 2 long times you're affecting and looking what happens in between.
Okay.
Okay. And thanks a lot for the very. Let's go for lunch. Okay. Thanks also to the audience via Zoom.